Okay, let's get started. And last time what we did, we done with the linear algebra and we moved to the second topics that I think I really believe that is needed for the machine learnings to better understand machine learnings. And the topic was the optimization. So I gave you some of the examples like people optimize and nature optimizes as well. And those are the motivations or examples to why we have to study optimization, or we have to understand optimization process. Here in the mathematical form, there are three key components. The first one is objective functions, and second thing is decision variables or just unknown variables. And the last thing is we might have some constraint on decision variables as well. So these are three key components. Whenever you have any kind of problems, and at the same time you decide to let's solve these problems or attack these problems using optimization method, then you have to identify. Given say engineering problems, you have to identify which one is objective functions, which one is decision variables, which one is constraint. That identify procedures, we call it modelings. So the first thing is modeling for the optimization problems. And the second procedure is that once we're done with the modelings, we have to find the optimal solutions. We have to solve that. So today, that's basically what I'm going to do. And this one here is there is some specific mathematical models or form to represent the optimization process. Here we have objective functions to minimize it, because if we have maximization problems, we just have minus sign in front of the objective function, so we can equivalently transform from maximization problems to the minimization problems. So it really doesn't matter. And for constraint, we call it subject to. We use less than equal to. That's the common practice. So we have the inequality constraint. And again, if we have the other way around, for inequalities greater than less, we can multiply the negative or minus sign, so we can, again, it's equivalent to transform it to the standard or mathematical optimization problems form. And even it's for equality as well, so we can have two inequalities, so we can have that. And there are many different types of optimization problems. Maybe the simplest that you can think of is unconstrained and constraint problems. Is too obvious. And another division for that is maybe we can think of convex problems, non-convex problems. I didn't explain what the convex is yet, but basically, that's what I'm going to do from now on. So that's where we stopped last time, and let's start with convex optimization problems. And of course, we have what is convex problem is the reason that it's extremely useful and powerful subset of optimization problems. And the definition of convex optimization is that, so this is, the general optimization problem models. And if X is convex functions, and the feasible reason C is, the space that the decision variables can have is if that's a convex set. So there's actually two constraints. Two constraints has to be satisfied in order to say that this is a convex optimization problem. I didn't explain what the convex functions and the convex set yet, but I'm going to explain them in a minute. The reason why we talk about convex optimization is that the key property of that is that if all the local solutions are global solutions. So say we find some of the solutions to satisfy, to find out the convex optimization problems that is guaranteed that that's a global optimal solutions, which is extremely useful. Okay, so let's move on to what's the definition of convex function and what's the definition of the convex set. Before that, I need to show some of the linear interpolations between 2 points. I mean, that's something that we need to define the convex functions and convex set. That's why I want to discuss this one. Suppose we have 2 points in the linear space. I mean, it doesn't have to be 2D or 3D. Say it's n-dimensional space. We have 2 the data points. Then, like this is x and this is y. And suppose this is the origin. Again, is in order to visualize it, I draw it everything in 2D space, in 2-dimensional space, but it doesn't have to. It's a you can think of it's a generalized n-dimensional space. And I want to know what's the, say, theta plus, or you can think of alpha and beta. So we have 2 vectors, and one of them we multiply. This is alpha is, I mean, scalar value. That means it's a stretch, right? We multiply alphas for x, we multiply beta for y. It's a scaling. And at the same time, and maybe I would say like that, if alpha and beta, they are both are positive, and the sum of them is equal to 1. If we have such a kind of conditions, then the geometric or physical meaning of z, what's the physical meaning of z? You can do same like here. What you can do is that like theta x plus theta y, and that's basically these 2 are equivalent. You can say alpha and beta, and summation of them is equal to 1, or you can define it as theta and the beta is 1 minus theta, are the same. And in that case, what's the geometric meaning of z? Anybody? What's the, so, and here, as you can see in the title, is the linear interpolations. So let's think about this, the figures that I draw. So we have x and y. So let me see. Z is that, right? This is the, so z vector is y vector plus this one. Let me see. This vector is x minus y. And it's smaller than, so probably is smaller than 1, but it's, again, it's positive. And we can rearrange it. Right? So now we can see that the meaning of this in z is that we can represent all the data points between x and y by changing the theta. if theta is 0, that means here. If theta is equal to 1, that means z vector is equal to x. And if, like, say theta is like half, probably like in the middle, this will be in the middle point between x and y. Okay, maybe like 1/3, then probably like I would say this is the z data points. I mean vector. So here, what I want to emphasize that if we have, I mean, this kind or this kind, two vectors and the scaling, but we have to have this kind of specific conditions on top of it. Then you have to you have to see that you have some insight that z is a linear interpolations between two given vectors. Right? With that in your mind, let's move on to the definition of convex functions and convex set. Right? What's the convex means like that. This is convex. I mean, everybody, this is convex and this is concave. Everyone knows that if we ask you to draw the convex, probably you're gonna do like that. But the problem is that we have to define it in a mathematical representation. What's the mathematical representations for in order to show that some given function is convex? And the idea is that, say this is convex and we have two data points and linear interpolations. All the data points in here is greater than the function of, say this is z, and always like greater than or equal to. So that's the definition of convex function. And we can write it down. Any x and y, two data points or two vectors, and theta is just, I mean, scalar values between 0 to 1. And this one is z, actually, linear interpolations, and f of z. And here, this one is y, f of x and f of y. Again, it's linear interpolations. So basically, looks complicated, but comparing these two data points. And key thing is, in this side is always is greater or equal to. That's the definition of convex function. Right? And let's move on to convex set. And probably, if I ask you to draw, I didn't give you the exact definition of convex set. But if we ask you to draw the convex set, probably you guys can draw. Let me see, like that. I mean, this one is not like convex set. You already. The reason why is that in this part is concave. So again, the thing that we have to ask is how can we, I mean, we kind of know what's the convex set, we can visualize it, but the question here is how do you represent it in the mathematical way, right? So again, the idea is that if that's the convex set, any two data points and the linear interpolations are within the set. So let me show you all the data points are within the same set, but in India is for the non-convex set, probably like say here is within the set, in the same set, which is okay, but some of them if we have two data points here, these data points are not out. Sorry. These data points are outside. It's not does not include it. It's not within the, so it's outside. We call it a non-convex set. So for the definition, the formal definition of mathematical set is that any two data points within the set, linear interpolations of them should be located in the same set, within the set. So that's the definition of convex function and convex set. I think you kind of, I mean, if you understand linear interpolations like that, it's not that difficult to I mean, because once you can visualize it, and the only thing that I did or that we did is that visualizations we convert, transfer it in the mathematical representations. That's the only thing that I did. So again, for the keep the convex functions and the convex set definitions in your mind. Let's move on to the how to solve the the convex optimization problems. So again, let's say that the second step is we have to find out the solutions, right? That's the key step. I mean, so let's think about how do you solve the problem, optimization problems. And once you have, I mean, start with the simplest problems. Using that problems, probably you can get some insight. So here I'm going to do the similar things. For me, I guess the simplest problems for optimization is probably unconstrained. So don't worry about the constraint. And the number of decision variables, like the simplest one is 1, right? So start with unconstrained and one-dimensional case. So we have only one, like unknowns, x. So minimize maybe like f of x, and say f of x is like that. So using this one, again, I'm saying this is the simplest thing that we can think of as a convex optimization problems, or it doesn't have to be. It's any kind of convex, any kind of optimization problems. And you have to see that, okay, I see x is probably it's a decision variables or unknowns. We have only one, and f of x is objective functions. In that case, probably if that's the minimization problems, probably this is the optimal solutions. Okay, I mean, once you draw the plots or figures, once you are able to visualize it, it's not that difficult to understand. Right? That's why I want to start with the simplest one, because if we have constraint and high dimensional space, nobody can visualize. It's too complicated. So let's get some insight using these examples to find the optimal point. In this case, it happened to the minimum point x of star, which is the optimal solutions. We can look at the derivative of that functions, because the definition of the derivative is a slope, right? If we have some, like at this point, it's a positive slope, that means there's minimum points. And if you have negative slope, that means we have to move on the positive side to get the smaller value of that. And once we do that, probably like here, if the slope is flat, that means either there's maximum point or minimum point. I'm talking about the minimization problem. So probably it's going to be the minimum point for this optimization problem. So any locations that satisfy this will be flat point. I'm not saying it's either minimum or maximum. It's a flat point. That's obviously true. Right? So, I mean, don't worry too much about whether this is maximum or minimums, because once we have, say we have some derivatives as z is equal to zeros and find out the x of star, it's not that difficult to figure out that's the minimum or maximum point. So don't worry about that one too much. And again, for convex problem, like I mentioned several times, it's guaranteed to be global minimums. That's the only reason that we love, that's why we love the convex optimization problems. So here, say we have f of x is given as an objective functions. Probably the first thing that you need to compute or calculate the derivative of that objective functions and set equal to zeros. Find out there will be some candidate of optimal solutions. I would say it's candidate because you might have like this kind of objective functions. Probably these are the flat points. You might have several, right? So these will be the candidate for the optimal solutions, right? But the good thing is, if that's a convex problems, probably like that. So that's the only solution that we can have and guarantee that that's a global minimum points. That's we done with the simplest models, and I want to make it more complicated, right? To make it more realistic, or I want to expand it. So let's generalize it. Instead of have single decision variable, let's have multivariate. I mean, let's say multivariate functions. Let's say, let me move to this one a little bit. Suppose we have n decision variable, n unknowns. Those are the dimensions space that we are thinking. And I love to have in a column vector form. And this the decision variables. Instead of having one, now we have n decision variables. And suppose we have, I mean here, that's the, but in many cases, I'm going to delete it. If the vector is too obvious, I'm not going to put the arrows on top of it. So make sure. And this one is another functions like that. And if you have only single variables, we computed the derivatives. But if we have more than one, like 2 or 3, and n-dimensional space, in the similar concept of derivatives is that it's a gradient. It's a gradient. We have to calculate the gradient of that objective functions in the multivariate objective functions. And what's the definition of a gradient? You guys, I assume that all like learned the gradient from the calculus, like when you freshmen or juniors. But if you don't remember, it's okay, don't worry about it. So here, let's think about we have f of x, which is the objective functions. Instead of having one decision variable, we have many. Okay. Then we can think of derivative of that objective functions with respect to the first decision, like x of 1. And we can think of like that. Derivative of objective functions with respect to second decision variable, which is x of 2, right? And in order to imagine that's like surface in 3-dimensional space or n-dimensional space, if that's the minimum point, we have to have flat all the directions. So this one has to be zeros if that's the optimal point, and this one as well. For all of them, That's the condition needs to be satisfied in order to be candidate of optimal solution. And these, again, if you have more than one, I love to have that put them in a column factor. And actually that's the definition of gradient. So that's the definition of gradient. And say for multivariate optimization problems, compute the gradient and set that is equal to 0 vector. So actually this is 0 vector, because on the right side we have all the zeros. Right? For the single case, probably you will say f of x equal to 0. For multivariate, you do the same thing. So that's the only thing that you guys need to remember it. Whether it doesn't matter, it's a single variables or multivariates, always think about the gradient and set that to equal to 0. That if you find out that solutions, there will be candidate of optimal solutions. And let's find out. Let's take these examples to how do you calculate, how do you compute them. So let me ask. So let's consider this problem. Let me ask, how many decision variables that we have in this case? How many? What's the dimension of inputs, not the dimension of decision variable? Anybody?
2.
Good. So we have x of 1, x of 2. And we need to compute the gradient, right? So let's do so this partial derivative, say 4x1, and for x of 1, x of 2 is like you can treat it as a constant. And here x of 2 minus 6. And for this case, 2x2 plus x of 1 minus 5. So that's right? And probably I can have like that, zeros. And we know that we can compute it like right? We can inverse it. So we can find out the solutions. That's the exact solutions or direct solutions. Suppose, say, we have objective functions and with the closed form expressions, and at the same time, like suppose that we can compute the derivative, partial derivatives or gradient of that, we can find the solutions like this. And here, like I said, in some cases, it's possible to analytically compute x of star, like just the example that I demonstrated. And let me ask, do you think this is convex problems or not? What do you think? What do you guys think? If that's a convex problems, the optimal solution that we find out here is going to be global. If we don't know whether this is on the convex or not, we don't know it could be the local minimums, not the global minimums. We don't know yet. But I'm not going to go in details, but it turns out the convex problems. It's a quadratic functions, right? So this is one of the example of convex optimization problems. And Another way that we can do is let's think about matrix derivatives. What we mean by that is that, say we have y is a of x. Here I represented a is a matrix. Here is some kind of vectors. Okay, and then actually this is probably I will say gradient of y. And gradient y is A transpose. I mean, let's say you have AX. I mean, this is this scalar case. We know that it's A, right? It's pretty much, but somehow we have transpose. Somehow. And I want to give you, say, I don't know, let me see, like this one. Let's think about this one as examples here. We know that 2x1 plus x2, 3x of 1 plus 2x2, and gradient f is that. No, this is not the case. Let me see. Let's think about this case. We know that 2 over x1 and x2, and gradient is that x of 1, x of 2, and 2, 1. So I define it, this one as A matrix, and this one is A transpose. So remember it, whenever you have matrix and the vector multiplications, and gradient of that is A transpose. And the second example is that X transpose A, if that's a gradient, it's A. And X transpose X, let's do this one. Let me say X is X of 1 and X of 2, and transpose is X1 and X2. X1 and X2 is X1 squared, X2 squared, right? And the gradient is that 2x1, 2x2. So it's x1, x2, 2x. So it turns out this. In the scalar case, we always in here is I'm talking about the matrix because now I want to move from the scalar to multivariate linear space. So now I hope you guys to get familiar with matrix and vector like operations and gradient in the vector space. In the scalar case, it's 2x, right? This one is here. This is a scalar. This is vector, and in the vector space, this one is acting like x squared, but it's x transpose x. I hope you guys to see like relations and like similar patterns in the scalar and the vector space. And another on the last is that suppose we have x transpose a x, and here this one is let's say I want to give you examples of that. And if you let's compute this one. Like that, 2x of 1, x2, 2x, x1 squared, x of 2 squared. So what I want you guys to looking at is, say we start from this is x squared, This one is x1 squared, x2 squared. But what if I want to do some scaling factors here? I want to have different weights, like coefficient. Then we can introduce a matrix here. You hope you see the patterns. Or patterns like that. So let's do the quadratic. Let's do compute the gradient. It's gradient 4x1 to x2. That's gradient. And turns out, say this looks like weird, but it's let me say A matrix is like that. So AX plus A transpose X. Actually here A is a symmetric matrix. So in that case, if the A matrix is symmetric, like, right, then A is 4, 2, x1, x2. We can compute it for x1 to x2, which is same as here. Here, there's no like theory behind. So I just want you guys to know that in the multivariate case, we do matrix and vector multiplications or matrix quadratic forms, and the gradient you guys can compute it, but using that, the tables, you don't have to memorize it. If you need it for the homework assignment or exams, probably I'm gonna give you the table, so don't worry about it. But I hope you guys to understand the theory. What's going on here. And let's revisit this case again. You want to do direct solutions, and I want to have, this one is very, let me see, X, I'm going to define it as a vector, column vectors. What I want to do, I got some like, and here we have, I will say 1.5 and minus or plus, and basically what I did, X transpose AX plus G transpose X. That's what I did. And make sure you understand this process, the multiplications. The only thing is just do it by your hands. Not that difficult. And we know that gradient of this guy is just, whenever you see this one, looking at this lookup tables, and AX plus A transpose X. And this one, like, you can use this one, and it's a transpose it. So the transpose is equal to, right? And I have to set this is equal to 0. And we know that A matrix, again, here is it's a symmetric. So 2AX and A matrix twice 3, 4, 1, 1, 2, X equal to minus, let me see, and we could have over there is like that, right? So 6 and 5. So this one is exactly same as this one in the previous case, like what I did it. So here I for direct solutions to compute it to derivatives or gradient, I gave you two different approach. I mean pretty much all the same. The first thing is for each decision variables, you can take the partial derivative with respect to each decision variables, or put everything into the matrix form, and using that, the lookup tables that I'm giving you, probably this one is another way that you can compute it, the analytic solutions for direct approaches. Right? And I'm going to show you some of the examples which is you're going to see very often in optimization problems or convex optimization problem, or even in machine learning. And this one, let me see, we call it A transpose X is a matrix multiplications, right? So this is, again, I mentioned so many times, it's a linear transformation because we can represent it as a matrix multiplication. But what if we have constant or bias? That's not a linear transformation. That's not. But we call it as affine functions or affine transformation. So this one is affine transformations. I want to compute gradient is using that, and looking at here A transpose, so it will be small. I mean here is capital A, is a small a, transpose, and transpose is equal to itself. And for quadratic, now what I want you guys to get some insight is that this one is pretty much the similar concept of square in scalar, but in the vector you have, in the matrix or high dimensional space, you have to think of as like that. And if P is in the symmetric matrix, it doesn't have to, but if symmetric, or for quadratic, it has to be symmetric. But okay, there are a lot of some detailed stuff, but don't worry about it. And this will be the gradient. Again, using that, and this one is using that one. Once you just trust me, right? And but I want you to, like 2 by 2 or 3 by 3 matrix, you can just do some kind of to make sure that these are right. Do it with the simpler examples and just take it now. For after that, just take it for granted and use that one. And this one is first affine transforms, and the second is quadratic functions or quadratic. And the last one is here. What is this? By the way, what is that? I think we saw it last time. You guys remember, it's in overdetermined linear systems or system of the overdetermined, like we have, remember that? If the A is a skinny matrix, there's no exact solutions in general. In that case, we have to do approximations. And remember, like in like A matrix, we have column vectors and span, and that span space probably B is probably could be in the span space or outside of. Then in that case, we have to minimize the discrepancy. That's the definition of in two norms and squared. And let me see. Suppose this is like that and not, let me say, yeah, this is say E. Then for definitions, no, I don't want to do, this is actually this column vector, column vector. So that's the definition, is that like that. Or you can say it's inner product. So I want to do a x minus b transpose a x minus b, right? Then a x transpose minus b transpose a x minus b. Here x transpose a transpose. Remember it, when you have multiplications and transpose it, we have to change the order of that. Then we just do like that, x transpose ax minus x transpose a transpose b minus b transpose ax plus b transpose b. That's exactly what I got here. And these are like some matrix. I mean, here is a different, but you x transpose some matrix in the middle, we have x and x transpose, and we have some matrix and x transpose. We can use that one. And a transpose a is always right. It's a symmetric using the properties. Right, you can use that. And this one, let me see, x, we have again this one. No. We have this case. Again, a is here is a different. I'm just using that symbolic expression. A is some matrix. So that's the gradient of this least square problem. And let's move on to, let's revisit. Remember least square solutions. Last time I spent a lot of time to explain it and to find out the solutions. And that in that time I use this one, because I love to understand for myself, understand some the problems in like, I want to visualize something and then understand, to get some insight, to find out, to understand the problems and to find out the solutions. I guess here in the linear space and spend and minimize the errors between and utilize the projection linear operations. I mean, this is really, for me, I give a lot of insight. But we can see these least square problems as optimization problems, and it turns out that this is another convex problem, but we can define it, this one as objective functions, and I did that, and this, and we can get gradient actually like that, and here I just did it in the previous slide here, and we set equal to zeros to find out optimal solutions. And I didn't explain it, but we assume that we know that this is convex problems, and here the solution that we found is going to be global optimal, global minimum points. And let's say A transpose AX2, A transpose. I think there's some typo here. We have 2. I missed 2 equal to zeros. That means the zeros, and A transpose AX is A transpose Y. Then X is A transpose A inverse A transpose Y. This is exactly same as the way I got from perspective of projections in the linear space. Right? So it's okay to, you can get the solutions from this side or the other side, it doesn't matter, but I'm trying to give you 2 different approaches or 2 different perspectives to understand this. But only, I mean, the important thing is you have to memorize this one. I mean, you don't have to memorize it, but you have to understand. Right? A transpose A, inverse A transpose, and Y. That will be give us the optimal solution for, you can think of as a least square problems, or you can think of as a convex optimization problems, or you can think of as projections in the linear space, no matter what, right? All right, let's move on to so far what I did is a given objective functions using the gradient, and we can get direct method or direct solutions once we have closed form expressions. But as you can see, if we have more complicated problems, and it's not easy to get some closed form expressions, and at the same time it's not easy, it's not easy to compute the gradient, or I would say it's not easy to solve some optimization problems by hand. In most cases, you want to use computer to get solutions. So don't worry about the iterations yet. I'm going to explain it in what's the meaning of iterative or iterations in a minute. But for now, time, don't worry about it. But here, what I want to say is that I want to use a computer to find out the solutions. So here, more commonly, the condition that the gradient equal to 0 will have the analytical solutions. In that case, you want to have iterative approaches. So the idea is that, again, starting from the simplest case, suppose we have, I got the same examples that I explained it here. Say we have no idea of what's the optimal solutions, and probably the easy thing is that you can try guess, right? I think let's say, suppose that x of naught or x of 0 is, say, the optimal solutions. You can just have a random guess or educated guess. We don't know whether this is optimal solutions or not. But one thing that you can do is that compute the gradient or derivatives. If that the definition of this one is give us the slope, right? If you walk this way, it will be positive. I mean, you have greater, and if you walk the other side, the f of x will decrease. You go up and go down. How much? That information is in the slope. So gradient in the directions of steepest ascent, like how steep. That's the physical or geometric meaning of gradient or derivatives. I want to utilize that information to compute the optimal solutions in an iterative way. Let me go back to. It motivates, let me move around here. It motivates the gradient descent, not at here. The descent means the opposite meaning of ascent. What I'm saying is that, okay, we don't know, and let's start with the random initial guess, and we compute it. It's a positive. That means if I walk this way, we have high in a neighborhood. In the small reasons for that is we have, because we know the slope, we know that the y or objective functions will go up. And if you walk the other way, you know that the values will go down. That fact gives us that we hope we can make conclusion that this one cannot be the optimal solutions, because we are trying to find the minimal points. And we have to walk this way or that way in the next iterations. We have to walk this way because we know that the slope is positive. Okay, and what about this? So we can have its random initial point, right? And say we got some negative values for derivatives or gradient. That means in order to get the smaller value on the objective function, we have to shift to the right. So if the past, so let me show you. So this one is the initial gas where we are at right now, and compute the gradient. If the positive, if that's positive, we have to take the minus. We have to update it. We have to move that the candidate for the optimal solutions to the left. And on the other hand, if that's negative like this, then we have in negative times negative, that means we have plus, right? So we have to increase value of x. How, and for this is going to be the slope. How much? Probably we have some scalar values of alpha. It will be step size. Does it make sense? We updated x. For each iterations, we are not sure whether we have to increase or we have to decrease, but we can get some clue from the gradient. If they're positive, if the negative, in the way. And here, look at these animations here. This is like single step, and we have to repeat it. We have to repeat that process. That's why I'm calling iterative. That's why it's iterative, right? As we increase the number of iterations, we're hoping that the solutions or the right, it's getting closer to the optimal solutions. It's getting closer to optimal solutions. For us, like human beings, we hate the iterative process. We don't want to repeat something. But for computer, they have to. I mean, they love to repeat that process. That's why in iterative method, we want to utilize the computer. So we call it is a gradient descent method. Right? It's increased the number of iterations. We're hoping that the solution, I mean, the checking points is getting closer to the optimal solutions like this. So we have to repeat the process. That's the principle of gradient descent. And here I mentioned some vague part is that how do you define alpha? It's a step size. Let me ask, if the alpha is like large value of that, what's happening? And if the alpha is very small, what's going to happen in the iterative process? What do you think? That's something, the alpha is something that like users like myself, I can define it. I can say like 10 or like 0.001 is really up to us. Anybody? Alpha is step size in the gradient descent, and it really affects the converging process. Probably this will give us the better idea of how do you choose the step size alpha. And this one, don't worry about it, I will explain it in a minute. But say if alpha is too small, that means we have some slope, negative slope here, but we multiply by very small number of alphas, then we're going to update it with a very small amount of, so like this. So it's gonna take some time. That means we have to do a lot of iterations. All right. I want to see that the effect of the value of step size alpha in the iterative process. On the other hand, if the alpha is too large, then we're going to like jumping around. It's overshoot or even diverse. So it's really critical to set the right values for the step size alpha. In some cases, it's going to take a lot of time to compute because it requires a lot of iterations. If we increase too much, then it's oscillating. And in the research, there are many papers talking about how to choose right values for alpha step size. One of the options is reduce step size over time. That's one of the options. Instead of having constant value of alphas, we can change the value of alpha based on the number of iterations. The idea behind it is that at the very initial phase, we will pick up the random positions for X. We don't know whether it's close to the actual solutions or not. That's why we want to have huge movement. But once we kind of find out, right, it's located, the X is nearby, then we have to do small iterations. So at the initial phase, we have large value of alphas, and later on, we will get we will decrease the value of alphas in order to have small steps to get some small search in a neighborhood. That's one of the options. And you can think of a lot of papers on how to find the right values for the step size. How do you get make sure like convergence problems, a lot of issues here. But in these lectures, don't worry too much about how to find the step size, because just get some insight or ideas. Okay, so alpha is very critical for the gradient descent method. That's the only thing that you need to remember. So convergence problem. Here for convex problems, for non-convex problems. Like I mentioned several times, for convex problem, it's good. Local minimum is going to be the global minimums, which is extremely powerful. But I guess this is a very special case. Right? In many cases, or in most cases, it's going to be non-convex optimization problems like that. And we will get like here, minimize, that means I will get these 2 points. In that case, here it's maybe like a one-dimensional space. You can plot it so you can visualize. You can look at the graph. You pick this one is minimum point. It's too easy, but you might not understand why I'm talking about this difficulty of finding optimal solutions for the non-convex problems. But imagine, like, say you have 10-dimensional input space and you have to plot it for objective functions. That means that's like higher dimensions. You cannot visualize it, and you don't know. You cannot get some entire the surface for the objective functions. You have no idea. In that case, it's very difficult to that some kind of candidate for the optimal, so the candidates, whether it's optimal or not. It could be local minimums, but no, it's extremely difficult to find that local minimum is global minimums. Actually, it's almost impossible to guarantee that. So in many cases, you end up here, and you're gonna believe that you find some good solutions, but it turns out that there is better options for that, but probably nobody knows. Nobody knows. Right? And the worst thing is that for the gradient descent is you use a computers, right? So iterative method. And there are several ways that we can try to overcome these kind of issues. I would say I try, right? There's no absolute solutions for this, the non-convex and the converging issues. But what you can do, say in this multiple local minimum might exist, and the possible way that you can attempt or you can try is, because it really depends on whether we starting point. So we do, right? So we do random initialization. Sometimes project start from here, and sometimes you're going to start from here. So this is, in that case, you got some luck and you find the local minimum. In that case, it has to be global optimums. Here, you didn't get the luck, probably you're happy about it, but actually it turns out that it's not, it's a local minimum, it's not the global minimums. But good thing about it is that you're gonna ask computer. Computer is just repeated process. So we'll do, say, we try to starting the random initials, we do gradient descent, find the candidates, and you memorize that one, and you repeat that process. I mean, you reset it, and random initials again, you do that, and you just do multiple trials instead of just do gradient descent once. That's not that difficult because we're not going to do anything. We're going to ask the computer to do that. So make sure that if the problem that you have, optimization problems, if that's not the convex problems, you have to do this. You have to do this. It's not, this is not the options. Right? You have to do this. And out of that, multiple trials you will get, you might have one or you might have difference, and then pick the minimum if that's minimization problems. That's kind of this is not a theoretical way, this is like a practical way. But in many cases, I guess it's kind of okay to do that. Now let's visualize the gradient descent in high dimensional space. Here now, instead of gradient here, instead of derivative, now we do have gradient. I explain what's the geometric meaning of gradient here. And this is one-dimensional space, and this is two-dimensional space. I mean, in the decision variable is one dimension, we plot it in 2 dimensions. Here, decision variables are like 2-dimensional space, but once we have objective functions plotted, it's gonna be the surface in 3-dimensional space. And from random initialization point, probably gradient descent will give you this kind of path or another path. We don't know. That's why we need to do multiple trials to get. And let me see the definition of this. Means that, I mean, I want to go back to the gradient again to show you what's the geometric meaning of gradient. And one of the components might be this one, right? This means that we have, say we have 4 examples. This means that I will keep x of, I don't want to change x of 2 Only thing is that I want to change x of 1 small amount of it, and I want to see how much my objective function or f of x changes. Meaning that, say, x of 1 and x of 2, I fix x of 2. I want to walk, this one is the constant values. I want to walk x of 1 in that direction a little bit. I want to see how sensitive. So the physical meaning of this guy is that here in surface, I cut it in that way, and I'm gonna get this, the intersection part and curved, and guess that's the slope, in tangential slope at this point. That's the physical meaning of this. What about so 2? That means I'm gonna fix that one, maybe in that directions, right? So probably this will be the curve, and this tangential slope will be like that. Okay. So that's the geometric meaning of component of the gradient, gradient, and using that ideas and see all this one give us that all the gradient should be 0 vectors. Otherwise, if some of the components in the gradient descent, gradient is not equal to 0, that means in that component we can walk nearby to get the smaller value of objective functions. So we always have to flat. That means all the components in gradient equal to zeros. That's the idea. Okay, I'm sorry, I already had 3 minutes. And let me. So today, what I did is that using that the given convex optimization problem, I show you 2 different approaches to solve that. First one is a Dirac method, and second is iterative. But what I'm saying is that I'm going right after these lectures, just remember the iterative approach, which is gradient descent, because we're going to use that concept or that method a lot in machine learnings and deep learnings as well. That's the only thing that I want to mention and summarize it. Okay, I will stop here.